Hey everyone, welcome to another video in our factorization part of our quadratic expression series. Now, in this video, we're going to revisit a topic we looked at before. This was the idea of a difference of two squares. So we talked about this through the lens of expanding. Now in this video, we're going to take the patterns we learnt from that to think about, if we have a difference of two squares, how could we go about factorizing? Now I've just got an example here from our expanding portion so that we can re-expand this, just a bit of revision, and then we can also take what we've learned about the answer we get and then apply that to how we could pick up on some little hints to help us factorize this again. Now, if I want to expand this, I'm going to use what we talked about before, this FOIL method, where each of these terms end up interacting. So my x times x, and I'm going to go through this a bit quicker because we touched on this before. X multiplied by x gives me x squared. X times minus 3 gives me minus 3x. X times 3 gives me positive 3x. And 3 times minus 3 gives me negative 9. And as you may remember from the previous example, this and this are going to cancel out because minus 3x plus 3x just gives me 0. So my answer, I'm going to wind up with x squared minus 9. And we saw a lot of these different types of patterns coming up in our expansion video. So what we've just done is we have expanded. This is an example of expansion, going from this to this. Now, let's think about how all of these numbers, how this, for example, interacted with all of these things here. Because in order to factorize, we just want to go the other way. So when we eventually end up factorizing by the end of this video, we're going to, instead of going from x plus 3 times x minus 3 equals the final answer, we're going to go from here back to here. So what's one thing characteristic of all difference of two squares? Let's just make some notes about difference of two squares. Well, one thing we always saw happening was these opposite signs. And those opposite signs always led to this thing happening, this cancellation in the middle. Now, what else did we see? Well, we had all of the same terms here. So we had the same term here as we did here. Now, in order to think about factorization, the final thing we want to do is make a link between the answer here and the values in the answer with my ones from my binomial product form. What you may notice here is both of these terms are what we call perfect squares. We get them from multiplying two of the same numbers. And these perfect squares have something in common with the two terms in my brackets here. You can see that x squared, for example, is x times x. It is this term squared. Well, both of these terms squared. My 9 relates to 3 because 3 squared equals 9. So one particular thing we can note, because perfect squares always end up coming out the same way. They're a very special case of quadratic expression. Now, x squared minus 9. This is what we end up with as a difference of two squares. And it's in the name, right? Because here we have our two squares And the subtraction that happens, that is our difference. So the answer we get is a difference of 2 squares. And the 2 squares have an innate relationship with the terms in my brackets, because the terms in my brackets are the square roots of my difference of 2 squares. Think about it. The square root of x squared is going to be x. The square root of 9 is going to be 3. And the difference comes from the different signs, this plus and minus thing happening. So if we take what we know about this, we can apply the patterns that we recognize. We can apply this to factorizing differences of 2 squares. Now, this is a quick and easy way to do this. As we go through the later topics, we are going to pretty much confirm this in the long way. But right now, it's all pattern recognition. It's all looking at what happens every single time and applying what we know to factorizing. So now we're going from the expanded form back to the binomial form, the factorized form. So what do I know? Well, I know that in my final binomial product thing, I'm going to have opposite signs, because my answer is it is indeed a difference of 2 squares. Let's just clarify this. Well, I have my 2 squares and I have a difference, a subtraction, the difference between x squared and 4. So these are my 2 squares. All I need to do now is figure out what each of these is going to be. Now you may remember, look back at the previous example. The things in the brackets were always the square root of my squares, of my perfect squares. So x squared is a perfect square because 2 terms can multiply to give me x squared. And 4 is a perfect square because 2 of the same numbers can multiply to give me 4. So my square root of x squared is going to go here, and my square root of 4 is going to go here. Now 2 is the square root of 4. X is the square root of x squared. This is using the patterns that we've observed and going backwards, how we can factorize perfect squares. Now let's just check that we've done it right, because you're probably looking at this and going, well, how can you be sure of this? Well, let's just check. X plus 2, x minus 2. Expanding this with our FOIL method that we did before, x times x gives me x squared. X times negative 2 gives me negative 2x. X times positive 2x gives me positive 2x. So x by positive 2 gives me positive 2x. And 2 times minus 2 gives me negative 4. And once again, my negative 2x and my positive 2x are going to cancel out. What do I get as an answer? I get x squared minus 4, which is what we had up here. So I have factorized this the right way. And this is what we're going to do for all of the examples in this video. We are looking at, in essence, recognizing the patterns that we learned from FOIL and just going the other way. So let's try a couple more examples. Let's try example B. We are going to look at this question, 81x squared minus y squared. Now we want to see, is this a difference of 2 squares? Well, 81 is a perfect square, along with x squared that it's getting multiplied by, and y squared is also a perfect square. And we have a difference of these two squares. So we can apply what we've been doing up until now once again. The main things I know is I'm going to have opposite signs here. And now I just want to find the square roots of my perfect squares, and they are going to lay in these blank spots here. Now I'll do the easier one first. Y squared is a perfect square. What is the square root of y squared? Well, it is just y, because y multiplied by itself gives me y squared. Now the next thing I want to do is I want to find the square root of 81x. Now this is a little trickier, but it's not too bad. Now x squared, we get that from multiplying x by x. And what two numbers multiply to give me 81? What two of the same numbers? Well, that would be 9 and 9. And this is the factorized form of what we have in the expression up at the top. Because multiplying this and this, the two 9s are going to give me 81, and the two x's are going to give me x squared. So altogether, we're going to have 81x squared when we multiply these two 9s, 9x's I should say, and y squared when we multiply the y's. Now let's just double check again, and I'm going to do this for all of the examples, just so you can see that this isn't just coincidence. This happens every time. Now we're going to check this. When I expand, 9x times 9x gives me 81x squared. So doing my FOIL method, 9x times negative y gives me minus 9xy. Y times 9x gives me positive 9xy. And y times minus y gives me minus y squared. And you can see that no matter what the terms are, whether they're algebraic or regular numbers, the same pattern is going to occur, because minus 9xy plus 9xy, these two are once again going to cancel each other out. And I get left with, that becomes 0, I get left with 81x minus y, 81x squared minus y squared. I get the same thing here. And what we're going to do with these questions, you may notice the first thing we're always doing is checking for perfect squares. We want to make sure this and this are perfect squares before we can even think about proceeding. Now that line's important because that's going to affect our next example. Minus 32. Now, let's check. We have a difference, but do we have two perfect squares? Well, 2b squared, while b squared is a perfect square, 2 isn't, because we can't have two whole number, two integers that are the same multiplying by each other to give me 2. In the same way, 32 is not a perfect square, because we can't get two of the same number, two of the same integer number multiplying by each other to give me 32. So we're at a bit of a standstill, right? There's not a lot we can do here. But if we notice, I can do something with this 2, which is going to affect my expression here to leave me with a perfect square. And if I factor it out of possibly this number, it may lead me to another perfect square. So what if I factorize 2 out? I can say the highest common factor in both of these expressions is going to be 2. So this is kind of like a double expansion. I'm going to pull out my 2, and what do I get left inside my brackets? Well, b squared gets multiplied by 2 to give me 2b squared, and I have a negative here. What multiplies by 2 to give me 32? 16. So by taking the 2 out, I have isolated my perfect square. And look at this. The 16 now is also a perfect square. 16 is a number we can get from multiplying 2 of the same integers by one another. And once again, we have the difference of these 2 squares here. So what we're going to do now is we're going to keep this 2 out the front, and we're going to factorize the difference of 2 squares up here. And we're going to approach this in the exact same way. I have one being positive, one being negative. Remember, I need opposite signs for difference of 2 squares. And I want to first find what's the square root of b squared. Well, that's just going to be b. And the square root of 16 is 4. So I have found the difference, well, the factorized form of this difference of 2 squares. Now, this is a little weird. It looks different to the other ones because this is a harder question, but we can check it in the exact same way. We can check that we've done it right. But the main thing we wanted to do here was we wanted to isolate the perfect squares. We wanted to, because we didn't have perfect squares here, we wanted to pull a number out, a common factor out, to give us this nice difference of 2 squares here. So if we check this, let's leave this 2 here, and let's expand this thing in here just to check that we end up with our very first expression. That's how we know we've done it right. So b times b gives me b squared. B times minus 4 gives me minus 4b. 4 times b gives me positive 4b. And 4 times negative 4 gives me negative 16. Okay, cool. These two are going to cancel out, my negative 4b and positive 4b. So I'm going to rub these out, and I'm going to bring this along here. Those cancel out, so I get 0, and I'm left with this as a simplified expression. Now, all I want to do now is re-expand to make sure I've done this correctly. 2 times b squared gives me 2b squared. 2 times minus 16 gives me minus 32. I have done this correctly because I get spat back out what I started off with. As I've said many times before, to check factorizations are being done correctly, we can re-expand. And if we get the original back, we've done it correctly. Now we're going to do one more example. This one's going to be harder in the sense that it looks weird, but the same process is going to occur. Now we want to check, is this in fact a difference of 2 squares? Well, x plus 1 all squared, that is a perfect square because two things, x plus 1 times x plus 1, multiplied to give me x plus 1 all squared. So this is still a perfect square. And we know that 4 is also a perfect square. And we have a difference here. The minus means there is always a difference. So I have 2 squares, x plus 1 squared and 4, which is also a perfect square. So in my brackets, I'm going to write, okay, I have my plus, my minus. So I'm going to factorize this. Now, well, what I'm going to do here is I've written what I need to do. And what I'm going to do now, if you remember, I'm going to find the square root of this as well as the square root of this. I'll start with the 4 because that's easier. So square root of 4 is 2, square root of 4 is 2. And let's just shift these signs over here because I need more space. And my x plus 1 is going to go here because x plus 1 is the square root of x plus 1 squared. Now, you may notice this looks a little bit different. We've done it in the same way, but it just looks slightly different. But that's okay. Now, if I take both of these terms, I can see there's a bit of simplification that can be done. Because I have x, I don't know what it is, but I have 1 plus 2. I know what 1 plus 2 is. In the same way, I know what 1 minus 2 is. So here I'm going to have x plus 3, and here I'm going to have x minus 1. Okay, so this is going to be my answer. And I'm going to do a little check here, but you're going to see we're going to hit a bit of a detour. So I may have to end it there because we'll be touching too much into a year 10 concept if we keep going along. But let's just get to a certain place. Let's get as far as we can go with the check, and then you're going to notice it's going to look a bit confusing, but I will return to this idea in later videos. But checking this, I get x times x is x squared, x times minus 1 gives me minus x, 3 times x gives me positive 3x, and 3 times minus 1 gives me negative 3, and I end up with x squared minus 2x, x squared plus 2x minus 3. Now, a lot of you may be a bit skeptical. You're saying, well, this looks a lot different to this thing up here. I can assure you it's the same thing, just presented in a different way. This can be achieved through a concept we're going to talk about later, which is called completing the square. The square. Which is beyond the scope of what we're doing in this course. But remember this idea, completing the square, we are going to come back to this. This isn't the last time you're going to hear this. But I assure you, this is the same thing, this bottom line, as this one up here. It just requires a bit of mathematical manipulation. But the process of doing this was exactly the same. We identified that this was a difference of 2 squares, so we wanted to find the square root of x plus 1 squared, find the square root of 4, and then just chip away at simplifying this. But this is how we can go about finding the difference of 2 squares based on certain patterns we pick up on from what we learned about expanding differences of 2 squares. The moral of a lot of this video and this entire series is that expansion can tell us a lot about factorization. And this way may seem like a little bit of a cop-out so far because we're really just looking at patterns, things we've observed before, and going in the other direction. But we're going to prove these as well when we start learning the other techniques for factorizing quadratic expressions. That's all for today, guys. Thank you so much for joining me, and I will see you in the next video.